we're going to look at 3 specific problems, okay? The first of those 3 problems, and these are all, at the end of the chapter, they put like the more challenging problems after they show each section, they put like additional problems. So I looked at 3 of those that were similar to old AP problems that I want you guys to investigate, and thought this would be like a good lead-in to that kind of a thing. 12th or 1/3? 1/12. So let's start on 95. Let's take a look at this one first. So we've got this system here, and this is again out of your text, so if you want to follow along or screenshot it from there to make it easier than writing it down. We've got a rigid body shown and consisting of 3 different particles. And the reason I picked this problem is because if I recall, last time we looked at that, remember the rocket wheel there? I think every group forgot to consider the rockets as their own point masses, and most groups lumped it into the disk I value. Remember, it was like a disk that was rotating and the rockets were on the end. So I purposely picked this one just to emphasize the fact that when we have point masses, we have to use just mr squared and not one of the I formulas. But let's go through this process. And it also connects us to kinetic energy and work in this problem. So we have these 3 masses connected by massless rods. So A, B, or AA, and then B, those segments are all massless. It's to be rotated about an axis that's perpendicular to the plane. Perpendicular to the plane through point P. So what direction would you say that axis is going? Or is it the X, the Y, or the Z direction, the axis that we're talking about here? It says perpendicular to the plane. Yeah, it's the Z axis. It's coming out of the page. So imagine, again, this axis coming out of the page, and these masses here, here, and up here, right? These masses are all rotated. Let me get this virtual background out of here. Sorry. I don't know, so you guys can't see my hand there. Just turn that off. Okay. So you got the, the 2 masses here, the 1 mass on the top. Well, here's the axis of rotation. It's the Apple Pencil, right, coming out of the screen. And these things are going to be rotating around that, okay? Because this is the axis here. The masses are given. The A and the B values are given. And the question says, how much work is required to take the body from rest to an angular speed of 5 radians per second? So let's kind of like work our way through what we're doing here, right? First, the question is how much work is required. So we know right away that we're trying to figure out the amount of work done. Now, what is given to us? What's given is that we want an angular speed eventually, little w, or omega really, of 5 radians per second. So if I have the angular speed and I want to know how much work is done, what else do I need to then calculate the work done via something else? That's really the question that's asked here. Like, we're going to have the mass, we're going to use those dimensions, that's fine. But what else can we calculate about this rotating body in order to help us? Yeah, very good, Chip. We can calculate the moment of inertia I. And if we get the moment of inertia I, how are we then going to use that along with omega to figure out the amount of work done? What does that give us, Chip? Good. Via the what? What is it really giving us? What is 1/2 I omega squared really? Forget work for a minute. What is that equal to? Good. Very good, Chip. So the key here is this. It says from rest. We need to emphasize that. Because it says from rest, we don't have to worry about the 1/2 I omega squared in the beginning because it's not rotating. Okay, and then eventually to an angular speed of this value here. So when we look at this problem, what we need to recognize is that we can't find the work done directly, meaning we can't do torque times theta. Remember how work is really force times distance for linear? Right? So let's go back and reiterate that. Linearly, this is work. But when we look at rotationally, we think of work as torque times theta. But we don't know the torque applied to this. We don't know the angle theta through which it rotates, so we don't have that information. So we can't use that formula. So as a result, we have to go ahead and use work equals the change in kinetic energy, which means the work done is the final kinetic energy minus the initial. Well, the initial is just 0 because it's not rotating to start. So inherently, as Chip said, we want to find the kinetic energy to find the work. Okay, we mean the final kinetic energy here. So as we said, if we want to find the kinetic energy, we need 1/2 I omega squared. So our final line here should say at the bottom, work equals 1/2 I omega squared. Now, we have omega, it's 5 radians per second, so clearly we need I. And that's why we go back to this statement here that said, what is I, right? I equals question mark. And when we look at point systems where we have several masses at a given distance from a rotating axis, we can't use one of these formulas from that table on the previous slide. Because that table on the previous slide is looking at solid objects that are rotating, right? Objects that have some dimension to them, whereas this is not that. This instead is point masses. So we want to find the I value for a point mass system. Remember, it's the summation of all the MR squareds. Well, how many MR squareds do we have? We have 3 of them here. Okay, we've got 3 different masses at 3 different distances. Oh, actually not different really. One of them that's doubled up, it can kind of repeat that itself. So let's see. I've got the I value is going to equal MR squared from the objects on the left, the right, and the top. Now, the object on the left, its mass is just 2m, and its distance away is a, and that's going to be squared. That's the mass on the left of the point P. The mass on the right of point P is going to be 2m, again, times that quantity a squared. So that takes into account the mass on the left and the right, and obviously they're the same, right? So instead of writing all this out, we can just double that first one there. Okay, we can just put a 2, let's use another color to show this. Let's put a 2 right in front of there instead. And that'll take into account both masses on the left and the right of P. But then I have to take into account the mass at the top, so I need to just quickly find out that distance. So let's draw a little dotted line in the diagram. And we have to figure out that height right there, right? The height of the triangle, which is really the distance that that object is from the rotating axis. So if we look at this, we've got a right triangle, right? ABC there. So as a result, we could say a squared plus the height squared equals b squared. Let's jot this down over here. A squared plus, I'm going to call this r. And now here's a question. I could take the square root of this, right, and get r. But in a moment, what am I going to do anyway? Right, take a look where I'm at. Right here. I could take this. Yeah, exactly. So I could take the square root and get r by itself, literally, right, by square rooting this and then re-squaring it later. So instead of doing that, I know that the mass is big M, and I want the r squared value, which is really just b squared minus a squared. Okay, again, I know it's not necessarily intuitive when you think about it, like why would you just skip this last step here, but really we don't need to square root it and then re-square it. Alright, so if we simplify this, we'll get I equals 4ma squared plus mb squared minus ma squared, which will end up becoming 3ma squared plus mb squared. So I'm just distributing this m to both of these guys here, right? And then collecting like terms afterward. Questions so far on this? Our last step is just to plug in numbers now. we have the M value is 0.4. We have the A value is 0.3. We have the B value is 0.5. Notice I'm changing my A and B to make sure that they're in meters. So we can plug in and get a value for this. I have that written down here. Hang on. What is the number? The number for I ends up becoming 0.208. Well, what are my units for I again? What are my units for I? How come? You know that? Very good. So no need to memorize the units for I if you haven't done so, because you can always think back to the formula, as Chip is saying, and just use mr squared. Very good. So that'll be the I value. We have omega, and we plug in and get our answer here for the work done. Okay, so this will be 1/2 times that I value times 5 radians per second squared will yield 2.6 joules. So again, what topics did we look at there? We looked at the concept of point masses rotating, and then we related that to the concept of kinetic energy, where actually the change in kinetic energy is then the work done. So we connected 3 of our different sections of that chapter, 3 of those different subtopics, so that we could see the overall energy or work done to cause this to happen. Now, had this problem varied slightly, you would then just vary your solution, right? If it didn't start from rest, well, then you wouldn't have this right here, right? The K0 wouldn't drop off. If you had a given omega that it started at, well, then you would have to use that second part of the formula and have minus here, right? Minus 1/2 I omega initial squared. And it would be the same I value that we plugged into both parts of the formula here and here. I mean, if the point masses had been changed, then the I value would be changed. But that's really all that can vary much in this problem. Maybe this was 3 point masses mounted to a rotating disk. Like, remember the rocket one that we looked at last time on the pivot lab? That's what that was, right? Those were 2 point masses, and they were mounted onto a disk. Then for that problem again, how do you find the I value? You would sum together the I value of the disk with the mr squareds from each point mass, and that would give you a different I value down here at the end. So keep in mind that if you have a system where there are multiple shapes, or multiple shapes, I guess, or multiple objects, I could say, we have to look at each of their I values and sum them together. But when one of those objects is out of our table, we can tack that on to the number we get for the point masses, right? For these 3 point masses, we can add on at the end here whatever the I would be for a rotating disk, if it were that case, or whatever case it may be. Similar to like a rod, right, that does have mass, and the rod is rotating about its center, right? I forget which one is that. Let's see what the number is for that. Is that one? So a rod rotating about its center like this, right, that's 1/12 ml squared. Well, if we had a mass at the end and another mass at the other end, we would have to do the 1/12 ml squared for the rod plus the mr squared from this mass plus mr squared from this mass. So we're constantly summing all of these I values using, it's really, remember I said superposition was the phrase, but it's using the concept of summing together the different I quantities to get the overall moment of inertia. Move on. Any questions on 95? Okay. We're going to look at 98 next. Let's take a look at 98 next. A yo-yo-shaped device is mounted on a horizontal, frictionless axis used to lift a 30-kilogram box as shown. The outer radius, big R, of the device is 0.5 meters, and the radius R of the hub, that inner one, is 0.2 meters. When a constant horizontal force, F applied, of magnitude 140 is applied to the rope wrapped around the outside of the device, the box, which is suspended from a rope wrapped around the hub, has an upward acceleration of 0.8 meters per second squared. So this applied force, right, is pulling here, and this box is getting lifted up. What is the rotational inertia of the device around its axis of rotation? So this is very similar to the types of problems that you're going to see on the AP exam, where you're given a bunch of info and you need to come up with the I value through experimentation. And that's really what this is. And that's how a lot of I values were determined. Now, mathematically, we showed how you can determine the I value, right? By using intervals, and we went through that whole process where we did like the I value of I think it was a thin rod about its end and a thin rod about its center we looked at that day. And we can do that, and that's fine. But what we want to focus on here is the fact that we don't have the mass of those hubs or the mass of the yo-yo shaped device they're calling that. So we can't find the I value by using a table or using those values. So we have to use an experimental approach. What formulas involve capital I that we can use to possibly figure it out, but again, not doing MR squareds? So what formulas in this chapter that we've looked at so far involve capital I? Very good. What else? Say again? Agreed. Very good. Anything else in this chapter involving I? I don't think we'll need another one, but I'm trying to think. I feel like there was one more that we looked at that I. Which of these two do you think we're going to end up using based on the setup of this problem? Why would you suspect that, Chris? So that's a good point, Chris. So let's write this out. So we're given here the acceleration of the hanging mass, right? And we're giving its linear acceleration. So because of the fact that we have this rope that's attached, we can automatically really find the alpha value as well. So let's start by writing the acceleration here. This is given, and this is given as 0.8 meters per second squared. We also know that the R value for the little hub is 0.2 meters. How can we relate these two variables to get alpha? What is our formula that yields alpha in these problems? Again, from A and R, how can we get alpha? Yeah, so we know that in these problems we have A equals R alpha. So A divided by R is equal to alpha here. So right off the bat we can start by finding the alpha value, 0.8 over 0.2, which is just 4, right? And my units for this are going to be radians per second squared. Now, let's think about sines, right? Sines. This system is rotating which direction? Clockwise or counterclockwise? What do you think? Clockwise or counterclockwise? Chris, you got it? Which one? It's going to be counterclockwise this time. Think about the bottom mass going up, right? So this bottom mass, right, has an upward acceleration. So if that bottom mass is moving up, right, then this entire system is moving that way. So we're going to see a counterclockwise rotation. So because it's a counterclockwise rotation, we've been calling counterclockwise positive, so we're going to keep this as a positive 4 radians per second squared. Had it been the other direction, we want to make sure that we recognize that that would be a negative quantity for alpha. The same is going to go for the torques, right? So we're going to see which way the torque applies its torque, if it's clockwise or counterclockwise, to yield a negative or positive tau. So I have how many torques acting on this system? How many torques acting on this system as a whole? What do we got? I see Tristan. Are you about to answer? Looks like he's trying to. Go ahead. Good. And can you explain which of the two torques? So we've got this force applied at a given radius length away, and we've got this force applied at a given radius length away. Now the applied force at the top, right, is at a larger radius from the center. The applied force pulling down is really just the weight of that object pulling down. But really, we have to actually find the tension in the cables, right? We need to look at the tension in the cables. So let's start this problem by looking, all right, F applied, that's an applied force directly acting. And if that applied force is acting at a distance of big R from the center, then we know that's going to cause it to rotate in a counterclockwise fashion. So again, we're referring to this one right here. This applied force would cause a counterclockwise rotation, which we'll consider to be a positive torque. So we're going to use this formula up here, like we said. Okay, we've got the alpha value. We're trying to solve for I. So we really just need torque net. So we have torque 1, which is going to be from this guy right here. And then we've got torque 2 from that one right there. Now torque 2 is going to be the tension in that cable. And the tension in that cable is going to be pulling it downward there. So we know that this is going to be minus torque 2. And again, that torque coming from that one is causing a clockwise rotation, which is why we're putting a minus. And this equals I alpha. But torque 1, that's going to be F applied times big R. But torque 2 is the tougher of the two. Not tougher, but we have to remember how to figure out that tension, right? Because torque 1 is easy. The applied force, that's a force value. Force times distance, right? We know that that's going to give us torque. So that one's not the hard one. We have F applied, it's given. And we have big R, that's given. But we don't have the force of tension in the bottom rope. Remember, this is not one continuous rope. Notice that? Right? This is not one continuous rope here. So we have to figure out what the tension is in the bottom rope. How may we do that? What do you think? I'll put in this little box in the middle here. How can we find the tension in that vertical rope? Chris, what are you thinking? Go ahead. I think you're muted, Chris. Go ahead. You're on the right track. We have the acceleration right now. You said the tangential acceleration, we would find it. I think we have that already though, right? So this is really, right, the tangential acceleration that we're feeling. But yes, so what might we do is my question, like more general. Use what? Use Newton's what? Yeah, well, one of Newton's laws pretty much, right? And we would, in this case, use F equals ma in the vertical direction. So if we're looking for this overall force, we have to recognize that this object wants to fall down, right? It wants to fall down. So the tension in the rope is going to pull back up here. So in this case, we've got tension minus the force pulling down, which is mg, and that's going to equal may. So we want to find out the tension. We can say tension equals may plus mg. And what is ay in this problem? Ay is this value right here. That's the vertical acceleration that this object is actually feeling when it moves upward, right, in that upward direction. So let's go ahead and figure out what we've got here. So in this part, we're going to have tension equals, and let's get a number for this. I have that number down here. it's going to be 318 newtons. 318 newtons, yes. Perfect. So why did we find that tension again? We found that tension force simply to plug it in up here because we know that this is going to be the tension in the rope times the little radius. And again, that equals I alpha. So this value right here is going to be applied right there. Okay? This value right here that we determined is going to be applied right over there. And then everything else is given in the problem. The applied force at the top was given. That was given as 140 newtons. The big radius is 0.5, the little radius is 0.2, so we can solve this for I. I'm going to solve it algebraically for I first. I equals F applied times big R minus tension times little r all over alpha. So this is a great approach when we're looking at an experimental way of determining the I value of any given pulley system, rotating disc hub arrangement, what they call a yo-yo shaped device, right? So this is a good way of figuring out the I value experimentally, not from using its geometric dimensions and the integration method that we used in class. So let's see what this turns out to be. Okay, gotta get 1.6 kilogram meters squared. Okay. And again, I'm plugging in numbers there at the end. We should all know what the numbers are in the given in the problem, and then the ones that we solve for, the tension and the alpha value we plugged in. And if you're doing this on the AP exam, you could either plug in those numbers, or you could even replace alpha, right, with A over R, and you could replace tension with MAY plus MG, and come up with the formula in a more explicit form in terms of all those variables. So either way is fine in a problem like this. Now, if they didn't give you something, and you're trying to calculate, there's a good chance that you should plug in all the expressions first because it might cancel out, right? Like say you were missing little r for some reason, maybe it would have canceled out. So when you get to that point in the problem where you're trying to solve and you're stuck because it feels like you're not given enough information, you might want to just pause yourself and say like, okay, what can I do here to make life a little bit easier? And sometimes that comes from plugging in all the algebraic expressions, not the numericals, and then seeing what will drop off. Any questions on 98? Okay. All right, let's keep going. So let's take a look at 100 now. And the reason we're looking at 100 here is because we want to look at a system that involves rotating thin rods through different axes of rotation. And I want to pose the question really at the end of like, why are our answers what they are? We're going to get two answers here, and the question is going to be, why are they what they are? And that sounds weird, but when we get to the answer, you'll see what I mean. But we're going to wonder why they are different or the same or what they are. So we've got two thin rods, each with a given mass, and they're joined together to form a rigid body as shown. One of the rods has a given length L1 and the other has a given length L2. The questions become the following. What is the rotational inertia of this rigid body about an axis that's perpendicular to the plane and passes through the center of the shorter rod? So the first axis of rotation we're going to put right here. Let's put that red dot right there. Then part B is asking us, what about when it rotates about an axis perpendicular to the plane that's through the center of the longer rod? So that'll be when it's right here. Okay? So we've got those 2 points, and we're going to take a look at them separately so we can figure out the rotational inertia for each of these arrangements, and then compare and contrast how they're different or how they're similar to one another. So let's take a look at the first rotation point. So again, this is for part A. So we're going to make that our rotation point first. And if we look at this, what do we have really? Well, first, we've got that shorter rod at the bottom, and that's rotating about an axis through its center of mass, right through the center of that rod. So if we want to look at this, and we want to go back to our table for a second, let's pause this and go back to our table. All right, so for this, again, rod, the shorter rod, and we'll call that shorter, and let's call this other one longer. For the shorter rod, we'll say that we have, in this case, 1/12 ml squared. And this is the shorter rod, so I'm going to, actually, I think the masses are the same, right? Yes, the masses are the same, so I don't have to put a subscript for that, but for the length, I'm going to put a subscript. So that's what our formula is for the shorter rod. That's all it's going to be when it rotates about the point in part A. How about the longer rod, though? How do we figure out the I value for the longer rod for still part A, right? So this is still part A. We're just putting these both together eventually, and we'll do part B down here afterward. How do we figure out the moment of inertia of the longer rod? Where is the axis with respect to the longer rod? Is it in the center now? I don't think so, right? Looks like it's at the end of that rod. So we can do one of two things. We can remember the formula for a thin rod about its end, because that is a very, very, very common I value. Just so you know. A thin rod rotating about its end. We did it the other day with the meter stick, remember, falling to the ground? That's a very common one. So you could memorize that, and that would be useful. But if you didn't memorize it, what would you use? Since it's not rotating about its center of mass, what theorem would you use? I say theorem on purpose because it was considered a theorem. We use the title. Yeah, so let's try with the parallel axis theorem to make sure that we know what we're doing here. Okay, but we could also remember what it is. But let's see what it is. So if we want something with the parallel axis theorem, we have to look at its I value about its center of mass plus mh squared. Okay, and the h value, remember, is the distance from where the center of mass is to where it's actually rotating about. So where is the center of mass? Well, the center of mass of the longer rod is right there. That's that green dot. And we know it's rotating, though, about this point here, not the green dot. So this distance right here, that's going to be our h value. Okay, that's going to be our h value right there. Now, the I value about the center of mass for a thin rod is this right here, right? This formula, but instead of ls, we're going to use the length of the longer rod here. This formula is going to go in right there. So this becomes 1/12 m, the length of the longer rod, squared, plus m times half the length of the longer rod, squared. So instead of using the number, right, the value, instead of using this distance from here to here, and that distance, if I recall correctly, is 0.25, instead of using 0.25 right here, I'm using this formula on purpose. I'm purposely writing L of the longer rod over 2, because that is the h value. Excuse me. And the reason we're doing that in this problem, I'm going to move down part B in a moment, is because I want to prove what the moment of inertia about a thin rod about its end of the rod is. And we're going to come up with that number so it's useful to use in the future. So this becomes still 1/12 m LL squared plus m. This will become LL squared over 4 now. 1/12 plus 1/4. 1/12 plus 1/4. Well, a fourth, instead in terms of 12, right, is going to be 3/12. So 3/12 plus 1/12 will give us 4/12. And 4/12 is really 1/3. Very good. And this is the formula that you probably want to memorize. Thin rod rotating, or add it to that sheet I kept saying, right? Maybe that sheet you should have next to you on the test. This should be one of them for sure. Thin rod rotating about its end. Okay, that's the key there. That's where that formula comes in. Anyway, the point is, what is the overall I value of the system? The I value of the entire system is going to be the I value of the shorter rod plus the I value of the longer rod. So part A, our answer, is going to be IS plus IL. And at this point we have numbers, right? We've got the lengths, we've got the mass given, so we can plug in for both of these and sum them together. So again, we're taking this answer plus this answer right here and adding those two values together. For the sake of time, let me just plug right down what we have here. It's going to be 0.019 kilogram meter squared. And again, this is all just for part A, rotating around the point shown in red. Questions so far? Okay. So note in this problem that we could have used the parallel axis theorem like we did, but we didn't have to if we remembered that it was 1/3 ml squared for a thin rod about its end. So a lot of the work that we did pretty much where? Here, let me highlight it in yellow. All of this work that we did in yellow could have been avoided if we remember that it's 1/3 ml squared. And this is just for timing, right? So when you're on the test in itself, you don't need to derive every single formula unless stated. Derive the I value for a thin rod about its end, and then part B would be like, use that I value. So unless directly, explicitly stated that you need to derive stuff, there are going to be certain entities that you can just, you know what, I've got it written down on a table, I'm going to utilize that equation and that value. And that goes for even what we did last class, or 2 classes ago, with rolling. Remember with rolling, we came up with the A value of an object rolling down a ramp, the acceleration of it as it rolls down. That's a really important formula, and that's one that you're not going to want to have to rederive each time. So that would be another one that you would jump right into the formula for that. All right, let's see how it differs for part B now. All right, so that was all part A. Let's see how this differs for part B. So part B, it's really a similar problem, but now we're rotating about that green dot on the diagram, right? Not around the red dot. So let's think about this. So here's our rotation point. So now the longer rod, right? The longer rod is actually rotating about the center of its mass, right? The longer rod is just going to be 1/12 ml sub L squared. So let's go ahead and write this down for part B. I'm going to slide the page over, make it a little smaller, move it up. Sorry for that. I think some of you are on your phone reading this, so I apologize if it's getting small, the problem. Maybe have the problem wording if you need it on the side. So for part B now, the I of the longer rod and the I of the shorter rod are going to be different. Let's start with the longer rod because that's the easier one now. Just like the last part, you know, the shorter rod was the easier one. So this is going to be 1/12 mL squared. And the reasoning again is because now we're rotating about the center of mass of the longer rod. So that just becomes the 1/12 mL squared, which is right off the table. But then what about the shorter rod? What about the shorter rod? It's clearly not rotating about the end of the shorter rod, right? Not the end. And it's also not rotating about the center of the shorter rod. So what approach are we going to take to find the I value for the shorter rod? If it were the end, we could jump right to 1/3, right? 1/3 mL squared if it was rotating about its end, but it's not rotating about its end. So we can't use a direct formula that we know. So if it's rotating about an axis that's not its center of mass, what theorem do we use again? The parallel axis theorem, yes. Okay, thank you again. So it is the I center of mass plus mh squared, and this again is for the shorter rod. The I value for the shorter rod about its center of mass is going to be the 1/12 MLS squared. That's going to be ICOM, again, for the shorter rod. And then what is MH squared going to be again in this problem? What is MH squared going to be? Chip, you look like you want to answer. Well, how far is H? What's H in this problem? Let's start by asking, what is H, right? What is H first? What does that mean? Like what, not number, but what is H physically? A more general statement I want you to answer with. I don't know, end of object, which object you're referring to even here, you know? Give me a more general statement. You were right in the beginning. The distance from the axis of rotation to what? Somebody want to help him out? He's got halfway, right? Right, this is the axis of rotation in this problem, so it's the distance from here to something else. It is. So remember, with the parallel axis theorem, here's the idea. If this rod, right, let's take a look at this rod here. If this rod were rotating about its center of mass, the answer is just 1/12 ml squared. But because it's not rotating about its center of mass, but another axis that's parallel to the axis through its center of mass, like think about, again, coming out of the page on the bottom and coming out of the page on the top. This is one axis, this is the other. The distance between those axes is h. So this would be the normal axis that it wants to rotate around. Maybe we think of it that way, right? Its own center of mass. But instead, everything is rotating about this point. So this solid right here, this entire rod, is going to rotate like around like that, right? So there's a gap between where it wants to rotate around normally, its own center of mass, and where it's actually going to rotate around. So this distance is like the R value for torque almost. You can think of it that way if it helps. This distance is also called h in the parallel axis theorem. So it turns out that when we go to do this last part here, this is going to be, again, just m, and h is really, again, still L2, or L, what do we call that, the longer rod, right, LL? The length of the longer rod over 2 squared. And what am I pointing this out for? Why am I writing it this way? And why am I not just using a number there? Because look, I want you to recognize this term right here. See this term right here? And then see this term right here? It's the same, isn't it? So when we used the parallel axis theorem earlier for the longer rod, we took its 1/12 ml squared and tacked on this. Now we're taking the 1/12 ml squared for the shorter rod, but we're tacking on the same value, aren't we? So in the end, when I add, ready? I'm going to add this right here to these two. It's the exact same thing I'm going to get when I add this to these two. So it turns out in this problem that when we do this and we do a little bit of math at the end, we get the total I value, right? The total I value is the IL from the top plus the IS from here. We're going to get the exact same I value. Okay? We're going to get the exact same I value. Now, why is this the case for this problem is my question then. Because I can change one thing, one parameter slightly, or one given, and suddenly these I values would not be the same. So what is the key about this problem that allows these I values to be identical? M, okay. Exactly. It's the same mass. That's the key to this problem. Because the L terms are all the same in these problems, right? We've got LL over 2, which is right here. And then we've got LL over 2 right here. Right? We've got LL squared. We've got LL squared. we've got LS squared, we've got LS squared. The 1/12, the 1/12, the 1/12, the 1/12. So all of these things are repeated over and over. And it's because the masses of the rods are identical. Because if the masses weren't the same, then this mass here, right, this mass would be the mass of the shorter rod. Take a look, right, the one I'm circling, mass of the shorter rod. And that would be different than this M right here, which would be the mass of the longer rod. Okay? So these masses right here that I'm circling would be different. If they were different, sorry, if the masses that I'm circling here were different, then we would end up with different I values. So it works out that these are the same thing. And that's the whole key to this problem, to recognize that you have the exact same I value because the masses of the rods were the same in this problem. That would be like a follow-up question. That's how you can expect the exam this year to be. They're really transitioning more away from like exact mathematical solutions, which has been the usual traditional way to approach this test, to a come up with a solution, explain the nature to the physics behind it and why the answer is logical or makes sense or happens to be the same as something else or whatever it is, or it's independent of something, right? Those are the kind of problems you can expect to be follow-up questions after you derive or solve the problem, derive an equation, whatever it may be. So I'm just trying to point that out, and that's why I really spent a little bit of time today on these three problems specifically, so we can understand the nature of the problems and why we're getting the answers that we're getting. So what I'm going to do is, I'm going to pause here, and what I'm going to do is I'm going to assign three problems, and let me screen share them with you real quick so you can see them and I can quickly address them. They're going to be on, where are they? Here we go. They're going to be on Moodle later today. Hold on 1 sec, guys. Let me just screen share this. I got it on screen share from here, actually. Hold on.